Okay, well, good morning, everyone. Welcome to the January edition of Saturday Morning Astrophysics at Purdue. I'm Jonathan. I'll be hosting the session and introducing our guest speaker, a professor of physics at Purdue, Dr. Jeffrey Gerber. And he's going to tell you guys the ingredients from the physics side of things of what physics needs to go into creating a solar system. So, without further ado, if Dr. Gerber, you want to take over and share your screen.
How to make a solar system. This is what we're going to talk about today. We're going to see what goes in. We're going to see why, when we talk about solar systems, and why, for example, on our graphic here, we've got something that's flat like a pizza and not spherical and round. And so this is a lot of our focus today. And eventually we're going to relate this to a topic that you might have seen popping up on social media and on some news sites. You might have heard that the planets are, quote, aligning. And so we're going to see, are the planets like actually lining up out in space in a line, or what exactly does that mean? A little bit about myself before we get started. I come from North Carolina. That was where I did a lot of my school, and my original undergraduate work was at this college here at Appalachian State that's up in the mountains. You can see it's kind of nestled in this valley in the Appalachian Mountains in North Carolina. And what you can see here, if you look closely at this campus, if you look at one of these buildings, sort of you see this building with all these kind of circular roofs going across it. And right from there is a little telescope dome. So there's actually a bunch of telescopes right there. And on the roof behind that dome, that roof actually slides back and gives about 12-inch telescopes. So I've done a lot of research and outreach and with those kind of telescopes. That eventually led me actually to Indiana University, where I did my graduate work and started working with some bigger telescopes out in Arizona. So here I am out in the mountain in Arizona, where I did a lot of work with this telescope that I'm standing in front of. This is a 3.5-meter telescope. And we also got to see sort of these other size telescopes, this 4-meter telescope here that you're seeing on the right. After that, I did some work in Germany at the Max Planck Institute for Astronomy, where I did research on stars and what they're made of, and began sort of building and collaborating on the next version of not necessarily telescopes like this, but these are going to be survey telescopes where astronomers don't go out to the telescope, but instead it just surveys the night sky every night. And we're expecting actually that project to finish up here within the next year. Our initial steps for getting that set up are going to come to fruition, and that telescope is going to be observing over 5 million stars in the sky. And so that's the kind of research that I do. After I was in Germany, I came here and became a professor at Purdue University, where I've been for the last few years. So what am I doing? What am I staring at with these telescopes? I like to stare at these objects that you see to the left. So these things are called globular clusters. They're big star clusters. As you can see, they're globular in shape. They make globes, right? Big spheres that we see. And I watch stars as they evolve. So I watch big red giant branch stars. So unlike our sun that hasn't gotten there yet, it's what we call a main sequence star. So a star sort of in the first phase of its life. I look at stars after they've entered sort of the second phase of their life, where they become big and red over here. And you can see those in the picture on the left. You see all these big red spots. Those are the kind of stars I care about. I figure out what abundances they're made of, or in other words, what kind of elements are in their atmosphere, looking at carbon and nitrogen. And that tells us what the star has done over its lifetime. And so we use that to figure out, tell us things about this low mass star evolution. So down here at the bottom sort of branch of what we have on this diagram, we watch these stars go from something close to our sun's yellow star up to a red giant and see how they've changed. And that's the kind of research that we figure out. But today, we're not going to necessarily talk about stars. We're going to talk about solar systems and how we make solar systems. So before I get talking, a lot of you have had a lot of experience. We talked a lot last SMAP. You talked about how stars were formed. And so I want you all to tell me, what is a solar system? So there's some images here to kind of help out of our solar system. Yeah, go ahead, Naomi.
Mhm. And well, it's die und das Planets sind. other small bodies like asteroids that are orbiting the star.
Sir, there we go. And there it was right at the end. The key thing that we want to talk about, a solar system is the system of objects. And we mentioned what those were, things like planets, things like asteroids, and other smaller bodies that we see in our solar system. And they're orbiting a star. So it's a collection of celestial objects, planets, moons, asteroids, and comets that orbit a star. You nailed it. Exactly what we have on the slide. So not only do we have our solar system,
Yes.
where we've got objects orbiting the sun, and so that's where the solar comes from, but we now know also that basically every star makes this system of objects. And these are exoplanetary, sometimes called systems, or people will stick the words exoplanet, solar system there to kind of get the same point across. So that's what you can see here. We've got these solar systems. We've got this image, though, of our solar system, and you see that in general, all of these planets are kind of flat. And that's the theme. That's what we're going to keep exploring as we go through today. So from last SMAP, you all talked about sort of as we talk about how a solar system gets formed. That's what we're going to start looking at. When you talked about, where's the water? And we talked about stars that are forming. What were some of the stages that these stars and objects go through? Does anybody know? What happens? How do we get this star at the center? Isabel, you knew you wanted to answer what a solar system was. You want to take a shot at this? How do we end up with something like this solar system here? What are
Well,
some of
with
the starting stages? What is the first thing we have before we get this nice shining star there in the center? Do you remember from last map? Maybe if you were at last map, or if not, maybe you know.
well, I think there's a lot of like dust and like material around
Yeah.
space, and it starts to like conglomerate and like fusion, and yeah.
Yeah, exactly. So we go through these steps. We start with this big dark cloud. We have some sort of cloud that's going to start sort of clumping together. Basically, gravity is going to kick in, right? Gravity is our force that brings everything together, that wants to bring all this mass. Mass attracts itself and brings it down and starts to form this pre-stellar sort of sphere. Eventually, we end up with this thing called a protostar that has this disk going around it with a star starting to form in the center as the stuff clumps together. Something called a T Tauri star is a very early star that has this big disk with these sort of big wings. They continue to collapse down until that disk starts, the leftover material that didn't go into the star that was out around the disk starts to clump together and form these planets. And so if we look kind of at a prettier version of that, we've got that here where we can see this giant cloud of gas and dust out in interstellar space begins to clump, begins to collapse down. And so dense cores, which are these precursor to stars, start to form. The cores condense into young stars, and then we're left over. The rest of this material, again, forms this disk. It doesn't stay in this nice circle. It flattens itself out into this disk over time. And eventually that disk forms these planets. So the big question we're trying to answer as we see sort of some of these protostars and what they look like eventually becoming these disks where you can see these rocky bodies start to clump together in there. And then eventually we end up with something that looks like our solar system with these planets individually around the star overall. And you'll notice these planets formed in that disk. So these planets are all in the plane. But our big question here is, why does this leftover dust form a disk around the star? So we had something that was nice and spherical, right? When we started off with our protostar clump, we had this big cloud of gas that eventually, it's got all three dimensions it can move in. It can stay a sphere, but why doesn't it stay a sphere? Why does the universe in general seem to make these disks? It's not just with these protostellar systems that eventually form these planets that are orbiting stars that end up in this nice flat plane. We see disks around stars that's in the sort of top part of this image on the right. We see disks around things like Saturn. So Saturn was a planet that had some leftover material that didn't go into making that planet. That material became a disk or going around Saturn instead of something that's spherically going in all sorts of directions. It was a nice flat disk. We've even got things like accretion disks, which means material that is being dumped onto a black hole. So this is material that's orbiting a black hole in the very bottom right of this slide. And that material also flattens itself out into a disk. It doesn't just orbit in any random direction. There's one plane that everything orbits in. So this is our big question that we want to try to figure out. Why does this leftover dust form a disk around the star? What is the physics that is causing all of this dust and gas to form disks? Why do we keep making disks out of things that are orbiting something at the center? Okay. So the way we're going to do that, we're going to go off into breakout groups to start, and we're going to look at our spinning orbiting object demonstration. So you're going to make a device that looks something like this over here on the image on the slide. You want to set up your apparatus. You should have your materials at hand, ready to go. You want to give your object some orbital motion. You're going to spin it around in a circle. You've got a worksheet where you're going to shorten and lengthen the string. So you're going to make some measurements there. And you want to then observe what happens. So how does that object's speed change as it orbits around? So you're going to measure the speed with something like a timer, count how many times it goes through. And we're going to see what we can observe about this orbit. What happens when we change the distance as it goes. Okay. So I'll let Jonathan take it.
So make sure that the string length from the head of the straw to the washer is like 10 centimeters. So you can just pull it apart and make sure you have a ruler, because we will need these values to be input in our worksheet. So we will need like exact lengths and the dimensions of your string and everything. So what you can do is just to get started. So the idea is here we will have this washer go around the straw in circular motion. So to do that, one obvious way is just to hold it and give it a little swirl, and this is how your thing will go. There the trial, and now trial 1, trial 2, radius, time, and number of rotations. So essentially what we are going to be doing in this experiment is measure this radius, and with the help of a stopwatch or a mobile phone or any kind of stop clock that you have, we will be measuring how many rotations of the coin or whatever your object is we have in a certain given amount of time. We want a long enough time so that we get rid of the initial wobbles, and also we don't want to be just rotating our coin around the straw for hours. So let's say anyone 20 seconds. Yeah, that's about right. So we can, let's say, just to be sure that we have got rid of all the external factors, and then we actually capture the washer in a good rotation. So let's say 30 to 40 seconds at max. So 30 seconds, 20 to 30 seconds, I'd say it will be a good time.
Trials. So and one thing we need to make sure is so there's some amount of effort we're putting into the coin. We need to make sure that that variable is staying as consistent as possible across the two trials, and that the only variable we're changing is the radius, right? So we're going to change the radius with pulling the string through the straw, but we need to make sure that we're putting the same effort in. So it seems like it might be easier to basically start with the string long, measure what it is with your ruler or whatever you have. And then, so we want 20 seconds for each trial. So set something like set something running like a 40-second timer and hold it for the same length and keep it spinning. And then at 20 seconds, shorten, and then count for another 20 seconds, and then measure what the shorter value is when you're done. And then you'll have two trials. So we're going to go for a long trial, and then we're going to go for a short trial. Which one do we expect to have more rotations? So let's think about that as we think of a hypothesis before we conduct our experiment here.
Yeah, well, I would expect that because the one with a shorter string means that the washer or object will be closer to, I guess, the center of rotation, so it'll rotate faster now.
Naomi knows about Kepler's second law, which tells us that as things get closer as they orbit, they tend to go faster as well, which is also correct. Right? And what we're learning about today is actually a direct application, and goes in and also explains Kepler's second law as well, as we'll talk about that later. All right, so go ahead and give your trials a go. I'll go jump into the other breakout room and see how their trials are going. And so it's difficult to get between the two trials. If the effort you put in is exactly the same, then we should see the number of rotations decrease and this number stay exactly the same that we're calculating. But if you put in more effort, then we should see this number that we calculate increase.
Yeah, I just tried it with a like lighter coin, and it's
Yeah.
really difficult to put the same amount of like force
Yeah,
into it.
that's the thing. You're probably gonna whip it around really fast. Yeah. And so that angular momentum change is coming from you. It then requires more energy on your part, or the coin might actually have a larger angular momentum that you're able to give it because the effort that you're putting in. And that actually what we call when we have, I don't know if you all have heard of things like, if I say force, does everybody know what a force is? Or can somebody tell me what a force is? No, Matthew nodded his head. He's got it, a push or a pull. He's got it in the chat, right? So a push or a pull, more generally, even it's an interaction, right? So we've got a push or a pull. Now, if we've got a force that's rotating, does anybody know what that would be? So if I don't just want to push or pull something, but I want to spin it, this value is talked about. Do we know what we call this special word for a force that's turning? It's a torque, exactly. So a force that causes a turn, we call it a torque. So we call it, for a car engine, we call it a torque because your engine is trying to turn the wheels. So a force can change a linear momentum. A torque can change a turning or an angular momentum. And so what you're doing with the straw is your hand's actually providing a torque. And so we're trying to keep that effort we put into the straw the same. If we were to put that into physics vocabulary, we would say that we're trying to keep the torque the same across both trials. Between the two different trials, how did the number of rotations? Was it bigger for the longer string, or was it less rotations for the longer string? When I left, we had a hypothesis that the shorter string was going to have more rotations.
So Naomi got
50. Okay. Which trial one is the longer string, right? Yes. Okay, great. Okay, so that seems to match our hypothesis. Less rotations for the longer string. Good. So that sort of all matches what we predicted going in. Then we have this value that we're looking to calculate. And what you should find, as long as you're able to put the same effort into both trials, and as long as you're able to keep that consistent, you should find that number that you're calculating, I don't know if we're still working on it, but you should find it's roughly the same for each trial. And if it is different, then what that indicates is that, which is difficult, it's difficult to do, but if you keep the effort the same in both trials, then that number will also be the same. But what often happens is when the string gets longer, we tend to put more effort into rotating the thing around. And so as we increase the effort, we're going to increase that number. So if that number is different between the two trials, then what it shows you is that you put more effort into rotating the object in one trial than the other. And what we saw in the first group, in the other breakout room, is that with the longer string, we tended to put more effort into that trial than we did with the shorter string, right? Good, we got angular speeds there as well. Great. So we've got this angular and rotational speed. We've got this sort of relationship that we're seeing that is either constant between the trials, or at the very least is related to how much effort we're putting in to each trial. Okay, and so I'm going to go back to our slides here. So we saw how the object speed changed. We then have this thing to calculate. Some of in the first breakout route, we kind of figured this out. We've got this value that we're calculating that is either related to the effort we're putting in, or it is staying the same between both trials. And that is because this thing that we're calculating is called angular momentum. So some of you, or at least in breakout room one person kind of already hinted at it, and the other breakout room mentioned Kepler's second law. Kepler's second law is a way to state that angular momentum is conserved. So you all might be familiar with that. If an object is more massive, then it takes more effort to move. And if it's less massive, it takes less effort to move. And if objects have more velocity, they're harder to change their direction than if they have less velocity. So that's related to the linear momentum of something. So if something is moving in a straight line, it has what we call linear momentum, and that is m times v down there. That's below that blue line on that diagram. It turns out spinning or rotating or orbiting things have a type of momentum called rotational momentum. And what that means is they've got some distance. Someone mentioned orbital distance in the second breakout room. In this case, it's the length of our string. There's some distance away from the center of a point. In our orbiting objects, there's some distance away from the center of the sun in our solar system, or from whatever star, if it's an exoplanetary system. For a top that's spinning, we look at the outer edges and how we've got this mass that's all spinning around a center point. And that gives us angular momentum that we write with an L, where it's related to that distance, how far away, squared, right? Times our, or the distance times our linear momentum, which is how far away we are from some object that's moving around. So it turns out that not only is it related to mass and velocity, but it's also related to the distance. What you might have noticed is that if you had to rotate the object, to rotate it at a larger distance, you tended to put more effort in. And that's because it takes more effort to do that. We call this effort, we figured it out in the one breakout room, but can anybody tell me, so the effort you're doing to rotate an object, does anybody know what that's called? Yeah, you mean exactly. Angular momentum is a conserved quantity, so it's got to come from somewhere. That means if there's nothing external to our system, it's going to just keep spinning around the same rate. If I want to change the angular momentum, then I have to put some effort into it. But to change angular momentum, if I want to change an object's momentum or how it's moving, or if I want to interact with an object, do we know what we call that?
Centripetal force, right?
Yeah, force. Well, force is the big word, yeah. And centripetal force specifically, that's a great point. Centripetal force is a big part of what we've got with an orbiting object, because centripetal force means a force that's pointing in towards the center of a circular motion. So over here, can someone tell me what our centripetal force was in our trials, in our little device? The string, yeah, Matthew nailed it. And so in the solar system, what is providing that centripetal force? There's no string tied to all of these planets.
Gravity?
It's gravity, exactly. Excellent. So gravity is the center pulling force that's keeping these planets moving around in this orbital motion with this centripetal force. So force is what's preventing these planets from shooting off into straight lines and just going away, right? They're staying inside our solar system. That's the force that's pulling. What we can also talk about when we try to rotate something, or if I try to spin something, we call that a torque. So that is a force that spins something, or a force that is at the distance from some sort of axis of rotation that we've got. So that is called a torque. You might have heard car engines described as how much torque they can provide. That's how much effort they can put into spinning the tires. And so if you saw two different values between your two trials, then likely what you did is you gave a different torque from your effort sitting in there on the string. So we've got this thing called angular momentum that we know has to be, yes, that's exactly it. You mean the sun's gravity is keeping everything in the system in orbit. So all of these things have velocity, and they'd want to move in these straight lines at all times, basically. If there was no gravity, then all of these objects would just shoot off in straight lines wherever they were going right now. Instead, the gravity keeps pulling them towards the sun, but their velocity moving sort of perpendicular in the other direction of that motion keeps them moving in a circle. So they're trying to shoot off and go away. The sun's gravity keeps updating. So instead of shooting off and going far away, they keep moving around in a circle. So the sun's gravity works exactly like the string in our trial. It's providing the same exact force that we call a centripetal force. Okay, so angular momentum is at play. It's something that all objects have. All right, so we've got angular momentum. So now thinking about angular momentum, can anybody figure out or think of why angular momentum might cause things to flatten into a disk instead of leave our big spherical ball of gas that we had before?
I feel like it's more like it takes more energy for the object to change direction instead of like just going with like the path they were going with, but like curved by the gravity.
Yeah, so it's something related to that. I like this idea of it takes effort to change something, right? So our big ball of gas, as these balls of gas and dust sit out there in space, before they make a star, it turns out that they're not just sitting there perfectly still. They tend to have a little bit of rotation in one direction or another. And so we just mentioned it takes effort to change, or that what we know about angular momentum. What's the big thing about angular momentum that we've talked about? It's a quantity, it's similar to mass, and maybe you've heard about energy and linear momentum in that it is, what is this big word we're going to look for? It's constant, it's conserved, exactly. It takes an outside force or effort to change it. So if this big ball of gas was rotating in some direction, do we expect it to keep rotating in that direction as it collapses, or to change? Yes, exactly. It's going to continue rotating. And so whatever angular momentum the ball of gas had at first, it's going to keep as it collapses down. And so as it keeps that angular momentum, as it collapses down, the radius is getting smaller of all the material. And so all that material starts spinning faster. So while the material collapses towards itself, it doesn't stop spinning. And so instead of being a sphere or being a tight, very tight ball, the spinning keeps it into and forms and shapes this disk. And so we're going to watch a video here. So what's the difference between centripetal force and centrifugal force? Ella, that's a great question. Centripetal force is this force that's pointing towards the center. So if we go back and we see all of these things moving around, and if we look at our disk, let's say my object on this orange sort of disk we have over here, let's say I've got a single object out here at the end of this green arrow that's tracing that black line. So I've got a force, there's a centripetal force that points from this edge of this tip in towards the center, right? That's centripetal. It's always pointing in. It's something like gravity or the string. A centrifugal force, can somebody, we talked about this actually in the other breakout room. Does somebody want to try to answer what a centrifugal force is? Somebody remember what we said? No?
I would say they're like opposite to each other. Like one
Yeah,
is trying to pull the thing towards the center, and the other one's like pulling apart from them.
yeah. So one is an actual force. The centripetal force is actually a force. It's something that's pulling or pushing. In this case, pulling towards the center. Centrifugal force is actually a little bit of a misnomer. It's not quite correct to call it a force. We call it a force because it kind of feels the same as a force. A centrifugal force comes from the fact that this object wants to keep moving where that blue arrow is pointing, but instead it gets pulled in. Because if you've been in a car and you've been in the back seat or something, and the car turns really quickly. So as the car turns, there's a centripetal force on the tires that is pointing towards the center of a circle that's following the motion that your car is turning. But you feel like you get pushed the opposite direction, right? So if my car turns to the right, it feels like I get thrown to the left. And that feels like a force. But there was nothing there that actually pushed me. What happened instead is my body wanted to keep moving straight, but instead the car underneath me turned away. And so I end up going towards the outside edge. And so we use this a lot of times in medical devices, actually. In centrifuges is a device that can separate objects based on their density in a test tube, because they feel getting pushed towards the outside edges of test tubes as they get whizzed around really fast. Or if you've ever seen a blender, and a blender on really high speeds, you see that liquid get pushed to the outside edges. So they don't actually clash. So this is a good example. And the reason they don't clash is because that centrifugal force isn't an actual force. So the centripetal force is there, pulling things. The centrifugal force is just a way to describe what we feel from the results. So we feel as though we get thrown towards the outside edge, or as if something was pushing us. So there isn't actually anything that pushes us that way. What's really happening is the car or whatever device is spinning tends to move out from underneath us. So centripetal forces are The actual force that's doing the pushing and pulling, it's pointing towards the center. This centrifugal, or pushing away, is actually a fake. There's nothing actually there doing the pushing. It's just our inertia makes us feel like something has pushed us the opposite direction. So this is a great discussion. Yeah, you all bringing up some great points about how we're going around in circles. So why does the universe create disk? We're basically going to sum up everything we said. This cloud, this sphere that we have, has an axis of rotation back when it was three-dimensional. The material starts to collide as it comes together, and some motion gets canceled out, but that rotation has to remain because the angular momentum is conserved. So instead of being flattened or compressed into a very small point, what happens is we end up with this disk that gets flattened out. And so we're going to show there's a good minute physics video that shows some great demonstrations of this. It shows some graphics to help sort of apply and summarize everything we've been talking about. So it's about 2 minutes. We'll watch it really quickly.
Our sun and the Earth and all the planets and moons and dwarf planets and asteroids and comets, the solar system in short, formed about 4.6 billion years ago from a nebulous cloud of swirling gas and dust, which coalesced thanks to the irresistibly attractive force of gravity. However, this nebula started off more or less as a big shapeless blob. So how did our solar system end up with all the planets and their moons orbiting in a flat disk? I mean, we've all seen the planetary model of the atom, which is definitely wrong when applied to atoms, but it also kind of suggests that planets might revolve around the sun every which way. So is our solar system somehow special in its flatness, or is the planetary model of the atom doubly wrong? Well, our solar system definitely isn't alone. Many exoplanet star systems are flat, a lot of galaxies are flat, black hole accretion disks are flat, Saturn's rings are flat, etc. So why, when there's all of 3D space to fill, does the universe have this preference for flatness? The answer has to do with two things: collisions and the fact that we live in 3 dimensions. Bear with me. Anytime a bunch of objects held together by gravity are zooming and circling around, their individual paths are nearly impossible to predict, and yet collected together they have a single total amount that they spin about their center of mass. It may be hard to figure out exactly what direction that rotation is in, but the mathematics implies there must be some plane in which the cloud, taken as a whole, spins. Now, in 2 dimensions, a cloud of particles rotating in a plane is flat by definition. It's in 2 dimensions. But in 3 dimensions, even though the rotation of the cloud is given by one plane, particles can whiz around far up and down from that plane. As the particles bump into each other, all the up and down motion tends to cancel out. It's energy lost in crashing and clumping. Yet the whole mass must continue spinning inexorably, because in our universe, the total amount of spinning in any isolated system always stays the same. So over time, through collisions and crashes, the cloud loses its loft and flattens into a spinning, roughly 2-dimensional disk shape, like a solar system or spiral galaxy. However,
so how does this relate to what you've heard in the news about the planets aligning? So this comes up every couple of years or so. These articles get thrown around that the planets are aligning, and they use graphics like this one, where they talk about all the planets lining up. Okay. But this isn't quite correct. The planets don't actually do this, right? So the planets aren't all lining up if you're hearing about the planets aligning. What's happening instead is relating to, since all of the planets are in this flat plane that we've talked about, what that means is, as the planets orbit around and as we observe the planets in the night sky, we see them trace out the same line in the night sky. And the reason they trace out the same line, all the planets are on the same line in the night sky, is because they're all in this flat disk. So all the planets are in the same disk orbiting the sun. We call this the ecliptic. So the ecliptic is the line that the planets trace as they move around in the night sky. The planets all line up on this thing called the ecliptic. Here's our ecliptic plane. Notice it's offset from the Earth's north celestial pole and south celestial pole. Does anyone know why that is? Yeah, Naomi. Yeah, the Earth is tilted. Yeah, and Naomi, we're going to say that?
Yeah.
Yeah, exactly. So Earth's tilted. So Earth is in this plane with everything, but Earth is tilted from that plane. And so the Earth's tilt means that our equator is off from the ecliptic plane. It's slightly off by exactly Earth's tilt, 23.3 degrees. But all the planets, you're going to find them in this ecliptic plane as they orbit around. So are the planets lining up? Not exactly. Instead, what's happening, they're not out there in 3D space lining up. What's going on this month and why we're seeing this news article is because we're actually at a time where during the night sky, the planets are such that you can see 6 of them in the night sky all at once. And so this is an image from Stellarium. If you're familiar with that, it's a program you can use to see what's going on in the night sky, wherever you are, whatever location you put into it. So right now you can see Mars, Jupiter, Venus, and Saturn all in a line as they're all in the ecliptic because we've got a flat solar system. If you had a telescope, so these are all planets you can see by eye. If you had a telescope, you could add 2 more and see Uranus and Neptune. But what the planets actually look like out there in 3D space is something like this. So notice they're not all in a nice, neat little line. Mercury is actually on the opposite side of the sun from Venus, and Mars and Earth are offset. And then Jupiter and Uranus are entirely different direction from Neptune and Saturn. So this is actually the spacing of the planets tonight, exactly what they would look like in 3D space. And tonight, if you looked in the night sky, though, you would see this nice little line that every so often gets called the planets aligning. But in reality, the planets are always on that same line because we've got this nice flat disk that we know exists because the physics behind it says there's got to be this conservation of angular momentum. This whole social media craze about the planets aligning, it actually comes up every 2 years. In fact, I quickly found an article from a couple of years ago saying that all planets line up, and then again, and this was something similar, where basically they followed the ecliptic out there in the night sky. And you can see the moon also sits on that ecliptic. So this is one thing, our sort of wrap up. We've got this conservation of angular momentum that causes disks to form and makes for flat solar systems and all sorts of things out there in the universe. The Saturn's rings are extremely flat due to conservation of angular momentum. So where else do you see conservation of angular momentum? I saw a good comment in one breakout room, maybe breakout room 2, maybe Ella, where do you have an example where you think you see conservation of angular momentum? Figure skaters, exactly. So Matthew said it. This is what we talked about. Riding a bike is another great example, Nathan. So where does angular momentum come into play with riding a bike? With the spinning wheels, exactly. Yeah, so with the spinning wheels, we see the angular momentum helps out as we ride a bike. And I'm going to stop sharing as we discuss here. So we've got our wheels and tires spinning. That's a great example. The wheels spin and they keep spinning, and so it's easier to balance on a bike when you're spinning those tires because those tires want to keep spinning in their direction because they have their conserved angular momentum. Isabel, what do you have?
I don't know if this is the right name in English, but according to Google Translate, it's spinning top.
A top, exactly. So a top's going to keep spinning, right? Once we get a top going, it stays upright and because it wants to keep spinning. And then when it slows down and stops spinning, it falls over because angular momentum is no longer conserved. Friction sort of took away its angular momentum as it spun, and then it fell to the side. But while you're spinning it, so you give it a torque with your hand, and then get it spinning, you give it some angular momentum, and it stays upright because it wants to keep spinning in that direction. Matthew mentioned figure skaters. So you'll see this if you've seen figure skaters spin, and this leads to something else you can try at home if you want. If you've got a couple of light dumbbells or some cans of soup or something like that and a rotating chair, figure skaters, you'll see them kind of rotate slowly with their arms and a leg outstretched maybe, and then they bring everything really close and you'll see them spin really fast. And that's because their angular momentum is conserved. So they give themselves some spinning while they're nice and outstretched. And then as they bring everything closer, they spin faster. And then when they want to slow down, they push everything back out. A whirlpool is another great example where we have things spinning. And if we get something to start spinning, then all of that motion as it comes together, the things towards the center of the whirlpool are going to start going faster and faster. With our ice skater example, if you want to try it at home, you can take those cans of soup or something, hold them in your arms outstretched, have someone spin you around in a rotating chair. And then after you've started spinning, bring your arms in together or the soup cans in together and see what happens as you spin. You'll probably start spinning faster because nothing is changing your angular momentum. So you spin faster when everything's close, and you spin slower when everything's far away. Frisbee toss, that's another great example. So yeah, if we want a frisbee to stay, if you've ever thrown a frisbee, if you want to stay nice and flat, what do? You give it some spin, you spin it, and then it stays nice and flat. If you try to throw a frisbee without spinning it, it flips and goes all over the place and doesn't fly very far as a result. These are some great examples. Other neat things, so these planets, because of our conservation of angular momentum, I mentioned they follow a path in the night sky because they orbit the sun in the same plane. But that also means you can use that if you're ever out looking at things in the night sky and you want to try to find planets, you can use the fact that they all trace a line to find more than one. So if you find one of the really bright planets like Venus, then you know to look in the same line to see if there's any others. And if along that line you see a nice red dot, then you've probably found Mars, because Mars is a red planet out there. And if you see any other bright dots, you're likely looking at Jupiter and or Saturn as you go along. So the ecliptic can be really useful when you're doing some observing out on your own, or if you ever want to point out what you think is a planet, it's got to follow that line because you know angular momentum means that all of those planets orbit in a disk. So that's how you make a solar system. You start with this cloud of material. It's got some kind of spin. We make a star, like all of you mentioned. And because of that gas has some amount of little spin to start off with, our angular momentum is there, and it means everything starts to orbit as it collapses, and we end up with these orbiting planets.